What's up, people? Welcome back, welcome back, welcome back. My name is Anoop, and yes, we are back with the third session of Radioactivity. Today's session is going to be super duper important, so stay till the end. Make sure that you take down everything that I'm saying today because it's definitely going to help you out in your understanding of this whole concept of radioactivity. So, welcome back once again. Hoping that all of your preparations are going good and you guys are putting in your 100%. That is all I expect, people. So welcome. This is going to be the session on radioactivity itself. So we're going to talk about what exactly is radioactivity, what are the things that has happened in the past that led to the discovery of radioactivity, and everything pertaining to the particular chapter. So today, in the last session, if you guys remember, we talked about isotopes, isobars, and isotones. Today we'll be talking about radioactivity. I hope you guys have watched the first two sessions, because only if you have watched that you'll be able to understand this a little better, because today we'll be getting a little bit more into the topic. So make sure that you know have gone through the previous topics as well. So that's it, people. Let's get into the homework question. So this was the homework question that I asked you in the previous session. The question was, what are isobars, and give one example. The answer to this question is quite simple, guys. What are isobars is nothing but the atoms of different element having different mass number, a different atomic number but same mass number. So they have different atomic number because they are two different elements, two different atoms or two different elements having different atomic number but same mass number. That is what is same mass number, right? Mass, I didn't write the same mass number is what is called isobars. Examples, you can give the example of chlorine, argon, because their atomic number is their atomic mass or the mass number is nothing but 40. And you can also give the example of potassium as well. Again, the atomic number for potassium is also 40, but the mass number of the atomic number of all of these is different, but the mass number is the same. Yeah. All right, sorry about that, guys. Anyway, so that the right answer is that they have same mass number but different atomic number. So that's it. With that said, people, let's get into the topic for today: radioactivity. Now, I'm going to talk about a small story, alright? So listen carefully. So the year was 1890s, alright? So there was this physicist known as Henri Becquerel. I really I'm not sure if I'm pronouncing it right. It's a French name, so even though it looks English, it's like Henry Becquerel, but then it's French, so it's Henri Becquerel or something like that. Now, so the year was 1890s, alright, and Henri Becquerel was a person who was very much into experimental physics. Alright, he was very much into experimental physics. His father was also a scientist. Even his son became a scientist. After his death. So he lived for about 55 years. Now, why am I telling about him? Let me come to the gist of the story. So Henri Becquerel was very much into fluorescent lamps. You know those fluorescent lights and those radiums and all that. So when you were a kid, I'm sure that you probably would have had those stickers on your walls, those stars in the solar system and all that, which basically lights up when it's dark. So those are the radiums and all that. So he was very much into these understanding about the fluorescence and all these kind of fluorescent materials and radiums and all that. People were very fascinated by this. People were very fascinated by this, and the whole, the first ever X-ray was also taken during this period. So people were very fascinated with these photographic screens and these kind of playing around with these fluorescent materials and all that. In fact, people used to make fluorescent lamps, fluorescent cups as well to drink wine and all that. So people were very much fascinated during that time because it's a very new material. So Henri Becquerel basically took uranium. Alright, so what he did was that he was playing around with uranium a lot, because uranium was also something which basically lights up. So it has this fluorescent nature. So if there's if it's it radiates that light when there's not enough, when the room is pretty dark. So he was very much fascinated by this. So he was playing around, he was working around with this uranium. So like I told you guys, at that time X-ray was just invented. So people were very fascinated by this fact that you can actually see through your bones. I mean, you can see the bones and all and get the image on a photographic plate. So he also wanted to see how would a fluorescent material react if you were to keep it in front of a photographic plate? You want to understand like what kind of image can you possibly get. So you want to understand what exactly is that. So what he did was that he took some uranium salt, he took a thick black sheet of paper, and then a photographic plate as well. Now, what he noticed was that when he put other fluorescent material, not uranium, but when he put other fluorescent material, when he kept the black paper and that photographic plate, he saw that there was like he left it whole night for 24 hours. He left it. Next day when he came and saw there was no change at all. So there was nothing formed on the photographic plate. So he understood that there's nothing. Basically, these fluorescent lamps are not able to produce any sort of image. There's nothing coming out of it, which is why they're not able to pass through the or those the emission might not be strong enough to pass through the black sheet of paper that you have. But when you took uranium on the other hand, and it did the exact same thing, even though that is also fluorescent, which basically lights up in the dark, the interesting fact was that he was actually able to see some sort of image, a black color image formed on the photographic plate. This is what got him thinking that it is not that uranium is just a fluorescent material. In fact, it is actually radiating some sort of rays, which is why it was able to form an image on the photographic plate. And that is how, guys, that is how the whole discovery of radiation started. So from this observation, he clearly concluded that uranium and the salt, the uranium salt that you have, the crystalline form of uranium basically, have some sort of radiation which can pass through the black cover and basically form an image on the photographic plate. In fact, it was passing through the photographic plate as well, and that is why you were able to see that particular image. This radiation was then named as the Becquerel rays or Becquerel rays. I'm sure my pronunciation is not right about his name, but I hope you get it right, people. So I hope you guys have a lot of French and everything in your third language. So yeah, probably you might be able to pronounce it better. So yeah, Becquerel rays is what it was called as. Then later on, guys, it was Madame Curie, Madame Marie Curie and all. Pierre Curie and Madame Curie, they together they started working with radiums, and basically that's how the whole the whole invention of radioactivity began. So it was him who actually started it. It was not actually Marie Curie, even though she was the more famous one, because she basically died because of these radiations itself. It was actually him who actually discovered all of these. So what they noticed was this, guys. So when you talk about an atom, a radioactive atom releasing some sort of emission, there are three types of radiations that are released. One is your alpha particle, the other is your beta particle, and the other is the gamma particle. So in other words, there are some positively charged particles, there are some negatively charged particles, and there are some uncharged particles. The positively charged particles are nothing but your alpha particles, which basically is nothing but helium atom. So helium 2 plus is what is released. So that is what is your alpha particle. Beta particle is basically when your atomic number decreases by 1. That basically when the beta radiations released, the atomic number decreases by 1. In the case of alpha particle, the mass number decreases by 8 and the atomic number decreases by 4. That is what happens. And when you talk about gamma particles, there is no change in the atomic mass or atomic number. There is no change whatsoever. So these are the uncharged particles that you have, which are nothing but your gamma particles. You have alpha, beta, and then gamma particles. Now, when you talk about radioactivity, there is a lot of misconception about radioactivity. See, guys, radioactivity is nothing but the emissions that is coming out from the nucleus. And it's a very spontaneous reaction. It's not like it happens for 5 minutes and then again it stops, and then again happens for another 5 minutes and then it stops. No, it's a spontaneous decay. This is what is called as a radioactive decay. So when a radioactive material is releasing this emission, that is what is called as a radioactive decay. So you have the alpha particles being released out, gamma particles being released out, and the beta particles also being released out. And those substances which undergo this kind of decay by a spontaneous emission of radiation, those are called as radioactive substances. All those substances which undergoes this kind of spontaneous emission, or basically they undergo the radioactive decay, those are called as radioactive substances. And examples can be uranium, radium, polonium, thorium, and actinium. All of these are different kinds of radioactive elements which are very much used in different fields. Anyways, now here's the thing, guys. The most important thing I would say is this. See, guys, radioactivity is something which is pertaining to only the nucleus. Alright, it is pertaining to the nucleus. So, for an atom, if it undergoes physical or chemical change like oxidation or anything like that, there will be no change in the radiation emitted by that atom. Why, you may ask? Because when you talk about physical or chemical changes, guys, it's all about the exchange of the electrons, right? Generally, it's the electrons that are getting exchanged, forming the bonds and everything. But like I told you, radiation, when you talk about radioactivity or radiations that are coming out of our atom, it is the nucleus that is actually releasing it, not the electrons. So the electrons have got pretty much nothing to do with it. It is the nucleus that is actually from where the radiations are coming out. So all these physical and chemical changes would not affect the radiation. This is one thing that I want you guys to be very, very clear of. All these physical changes, chemical changes that happens does not affect the radiation in whatsoever capacity at all, because radiation, when you talk about, it's basically the emission of radiation from the nucleus and not the electrons itself. Now, here's the thing, guys. Now, before I help you to understand this experiment, I have to tell you something. So, here's the thing, guys. Until the year 1911, all the chemists around the world believed in the model which is called as the Plum pudding model. So what is the Plum pudding model? Is nothing but basically this is what they thought the atom looks like. Until then, this is what they thought the atom looked like. So if when you see from the top, this is what it looks like. So you have all the positive particles just roaming around freely over here, and then you also have these negative particles also along with it. Alright, so you have the positive and negative particles, which are basically in like a small sea of pudding. The puddings that you eat, those desserts and all that. So it's like that. This is what is called the Plum pudding model. Now, all the chemists during that time believed this. Alright, they all believed that this is what the atom actually looks like. Now you guys already know from your first standard, second standard, you guys know what a picture of an atom looks like. So you already know that this is what it looks like. But back then this was not the case, because we had not proved it yet, because we had not known about it yet. So people believed that this is what was an atom basically. Now, in 1911, what happened was that there was a scientist called as Ernest Rutherford. Alright, so Ernest Rutherford designed an experiment such a way that what he did was that he took a particle which basically releases alpha rays or alpha particles. So he took an atom which releases alpha particles. He took a lead box, and basically placed the alpha particle inside of it. And then made a tiny hole in the front, okay, a tiny hole, so that the alpha particle that is coming out from that tiny hole itself, and it will be emitted out in a straight line. So this was the intention. What he did was that, this experiment is very interesting. So what he did was that he basically made a detector. So this is basically the detector which was basically going all around. So this big detector actually is like this. And this detector is also a photographic plate. It's also a photographic plate, alright. This detector is also a photographic plate to basically detect the alpha particle that is coming out of from the lead box that you have. The alpha particle, that is the atom that is releasing the alpha particle, you want to detect it, right? That is the intention. Now what he did was that he basically took a gold plate and placed a very thin gold plate and placed it in front of it. All right, a very thin gold plate and placed it in front of it. Now the reason why he chose gold was the reason why he chose gold and not other materials is because gold is a very malleable metal. You guys already know about it, right? Gold is a very malleable metal. And what they did was that basically took a thin sheet which has roughly about 1000 atoms, right? So because basically if you were to take the same thing of steel or any other material, it would have been much more. The number of atoms would have been much more. But they took a gold plate because it's very malleable and they can make a thin sheet out of it. So they placed it in front of it. Now what is the intention? See, this is the intention, alright? So the alpha particles that are going, if it is the plum pudding model, if it is a plum pudding model, that means that all the particles should pass straight through. Because why? First of all, alpha particles are very heavier, they're very heavy, and they can easily pass through all these materials. So what was the intention? So what they expected was that, so when you pass the alpha rays through this gold sheet, because the alpha particles are much more heavier, they should pass straight through and reach the detector, and basically all the rays should be able to, should be detected from that particular spot itself. Maybe there might be a little deviation, that was accepted, but not too much. But what they actually noticed was that the alpha particles that were released out, few of them were actually basically, few of the rays were actually going straight through. Some of them were getting deflected back, and some of them were also getting deflected in different angles as well. Now this is something that they did not expect. Now this wouldn't have happened if they had assumed that atom is basically the plum pudding model. If an atom was a plum pudding model, this shouldn't have happened, because alpha particles are heavy, so they should be going straight through. But that did not happen. That is when Rutherford told that it should not be the plum pudding model, but in fact this is happening because there must be some positive particles that is there in the center, and there must be a lot of empty spaces around the atom as well, or inside the atom itself. There should be a lot of empty spaces, because of which the alpha particles are going straight through. Because there were a lot of space in between, the alpha particles are going straight through. If the alpha particles came and directly hit the positive, positive will repel, so what will happen? It'll get reflected back, and that is why they were able to see some of the alpha particles rebounding back as well. They were getting rebounded back as well, and some of them were getting deflected in different angles, because you see, the alpha particle just goes, hits the nucleus, which is the positive particles, they get deflected in different angles. And this is how, guys, the current model of an atom came into existence. This is how we proved that it's not actually the plum pudding model, but it's actually this one. You can see that the nucleus and the protons, the nucleus that is there, which contains the protons and the neutrons, are there in the middle, and the electrons are revolving around it, and there's a lot of empty space as well between those. And that is how the Rutherford experiment, the Ernest Rutherford experiment, changed the way that we look at an atom, right, guys? And that is what I would like to tell guys, because it's a very important experiment, super important. If you've understood this, then everything else that comes after this will be super duper easy. So it's very important that you understand this. If you haven't understood this, make sure that you go back, scroll back for another five minutes back, and then check out the video once again, guys. Please make sure that you do that. It's very important that you understand this. All right, so this is how, guys, he studied the nature of radiations emitted by a radioactive substance. He was also able to understand, the alpha particles, that's how they understood that the alpha particles are positively charged. They were able to understand that because, you see that the positive will repel, so they were able to see that the particles were bouncing back, and some of them are getting deflected as well. Now, if I were to take a radioactive substance, and again I put it in a lead box and place it in a magnetic field, you see that the radiation that is coming out, the alpha, beta and gamma particles that are coming out, the alpha particles will deflect towards the left. The beta particles will deflect towards the right, and you see that the beta particles are deflecting far more greater. Why? Because alpha particles are much more heavier. Beta particles, on the other hand, is very light, so they'll get deflected more, and gamma particles will pass through unaffected at all. They don't care whether it's magnetic or electric field. They'll pass through undeflected straight from that particular electromagnetic or radioactive material. So like whatever the radioactive materials, whatever the radiation is for, wherever the radiation is originating from, it will pass through straight. Alpha particles will go towards the left, and beta particles will go toward the right. On the other hand, if you talk about a magnetic field, so this is what it is. So those which turn to the left are your alpha particles because they are positively charged, and the beta particles which are negatively charged will pass towards the right, and gamma particles, because they are uncharged, will pass through straight. If you were to pass it, put it in an electric field, so you place two electrodes, one is a positive electrode, then the other is a negative electrode. So here also you see that because the alpha particles are positively charged, they'll go towards the negative electrode because positive and negative will attract, right? Unlike forces unlike charges attract. So they'll go to the negative electrode. The beta particles which are negatively charged will go towards a positive electrode, and the gamma particles again pass through undetected or undeviated. They'll just pass through straight. This is also another thing that I would like to end the session with, guys. So this is the entire concept, people. So once again, alpha particles will, because they are positively charged, they'll go towards the negative electrode or the negative plate, and the beta particles which are negatively charged will move towards a positive plate or the positive electrode, and the gamma radiations will pass through undeviated, right? So yeah, people, that is pretty much it. If you are enjoying the session so far, hit that like button, hit that subscribe button, hit that bell icon so that you are notified of all the preview of future sessions as well. And if you want to have more such amazing sessions and gain 100% knowledge and gain 100% marks in your boards and your pre-boards, guys, we are here to help you out. Click on the Vedantu Pro subscription course, enroll into the course right now, where you have an amazing opportunity to learn with the best of the best teachers, where you have unlimited live session, lots and lots of fun with unlimited amount of quizzes as well. And those quizzes, trust me guys, are simply amazing, which will help you to understand the concept, and at the same time will also give you an opportunity to compete with the rest of the world and understand what are your weaknesses and what are your strengths, and make a proper decision accordingly. So that is what these quizzes helps you to do. You have leaderboards. You can, in fact, all of these sessions are recorded, and they are recorded such a way that even while watching the recording, you can actually take the quizzes while watching the recording and still check out the leaderboards while watching the recording as well, guys. How cool is that? While watching the replay also, it's an interactive replay. You can actually check the leaderboards and check out your quizzes, take part in the quizzes and see how good you have done or you would have done in that session. With all of these, guys, you can download all the premium content, every single handwritten note, everything that is pertaining to the chapter, everything that you need to succeed, everything that you need to improve yourself every single day. All of that will be available to you at your fingertips. You can watch the recordings, download all the notes, and with that, people, every single session you will have a set of 2 teachers, the master teacher and the class teacher, to help you clear every single doubt of yours. The class teacher's job is to make sure that every single doubt of yours is cleared inside the session itself. No matter how many doubts it is, 50, 100, does not matter. All of your doubts will be cleared inside the session itself. And yes, you have some amazing tests and assignments as well, guys. Some super awesome questions will definitely push you to your limits and help you to understand the concept much better. And more importantly, guys, I know that you guys are preparing for your exams, and this is the time for you to practice as many number of questions, as many number of numericals, as many number of question papers as you possibly can. And here you have an opportunity to do all of that in one single place. And here's the best part, people. You have, for the next couple of days, a 50% off if you use the coupon code AME Pro to avail the discounts. You get a flat 50% discount. That means that if you go for the 1-month program, people, the base price of that is 2,699. I know that it's a lot of money, but if you use the coupon code AME Pro, you get a flat 50% discount, and the price drops down to 1,350 rupees, which means that per session, which in that 1 month time you have attended about 200 sessions, that means that per session you are just paying about 6.7 rupees. Right, guys? So how do you enroll to the courses? Let me just show you how to do it. So what you have to do is basically, guys, first of all open up YouTube. Yes, go to we'll go to Vedantu 9th and 10th English. Yes, it's right here. So you click on that. I know that the sound is going to be a little irritating right now. Let me just turn off the volume just to, yeah. So yeah, click on any of the videos that you have. Click on show more, go to this option called as, go to this link, subscribe to Vedantu Pro right now, click on that link, and once you click on that link, guys, they'll ask you which grade do you belong to. Let's say you're in 10th grade. Once you click on it, they'll ask you which board do you guys belong to, CBSE, ICSE or Maharashtra. Click on the board, ICSE. You can check out all the things that I just told you. You can check out all the results, all the teachers will be teaching you in the regular sessions, and what you have to do after that is basically click on proceed to pay and enjoy the courses. So once you enroll in the courses, guys, you can check out all the all the classes that you're eligible for. You can check out all the recordings. Everything would be available to you right there itself, right, guys? So you can check out the link. description as well as in the pinned comment section. With that said, let's now solve some questions. Let's do it. Come on. So what we're gonna do right now is I'm gonna ask you a series of questions. What I want you guys to do is answer the questions honestly. Don't depend on Google Baba. Don't depend on your cousin or your parents or your sister or your brother. Do it yourself. All right. Use your brains. All right, and try to do these questions yourself. That's all. So let's go ahead and look at the first question, people. The first question is: a radioactive substance emits what? Emits radiation. Alpha, beta, and gamma rays simultaneously. In an order of alpha, beta, and gamma one by one, X-rays and gamma rays, or alpha or beta rays. The answer to this question is in 5, 4, 3, 2, 1 is actually option number D. It's either alpha or beta. Now here's the thing, guys. A radioactive substance cannot release or cannot emit out alpha, beta, and gamma simultaneously. That is not possible. Either it will emit out gamma rays or either alpha rays or beta rays. Now, if when you talk about, see again, guys, when you talk about radioactive decay, remember this one thing. Why I'm telling you is this, because radioactive decay is basically when when the radiations are basically the radioactive element undergoes a decay, and basically these emissions are the radiations are emitted out. Now, what you have to understand is this, guys. The final element that you're going to get once the radiations are emitted is going to be different from what you started off with. So in the case of alpha and beta rays, we've already told you that, so there's a change. Basically, in the case of beta rays, I told you that the atomic number decreases by 1. In the case of alpha rays, I told you that the mass number decreases by 4, and the mass number decreases by 8, and the atomic number decreases by 4. So because of this reason, guys, see that there's a change in the element happening. But in the case of beta or gamma rays, there is no change whatsoever. So option number D would be the right answer for this question. All right, I hope you understand this, guys. Moving on to the second question. A radioactive source emits 3 types of radiation. Which radiation has 0 mass? Alpha, beta, gamma, neutrino. You know the answer for this one, guys. In 5, 4, 3, 2, 1, gamma, people. Gamma has 0 mass, not alpha or beta. That is why you see that they also get deflected in a magnetic and electric field, whereas gamma, on the other hand, it has no mass whatsoever. Next one. Which French scientist is credited with discovering radioactivity in 1896? Is it Antonio Lavoisier? My pronunciation with names is superbly bad. Is it Henry Becquerel? Is it Louis Pasteur? Is it Pierre Curie? My pronunciations are bad, but yeah, you get the point, people. 5, 4, 3, 2, 1. The answer is Henry Becquerel. He was the one who discovered it. There was Madame Curie and Pierre Curie who did more research on radium and basically, brought it mainstream. Next one. The diagram in the figure shows a radioactive source as placed in a thick lead-walled container. The radiations given out are allowed to pass through a magnetic field. The magnetic field shown as X acts perpendicular to the plane of paper inwards. So arrow shows the path of the radiation A, B, and C. What are A, B, and C in other words? That's what they're asking. So A, guys, okay, let me start with A. A is nothing but gamma. A is gamma. B is nothing but alpha, and C is nothing but beta. So that would be the answer. So you have alpha. So the answer would be A is gamma, B is alpha, and C is beta. So the answer is option number C. Like I told you, so to the right hand side you have your alpha particles, to the left hand side you have alpha particles, to the right hand side you have gamma particles. So yeah, beta particles and gamma particles will pass through undetected, undeviated straight. Next one. Okay, this is the last question, guys. This is a homework question. Let me know what is the answer to the next session in the comment section. The question is it possible to deflect gamma radiations in a way similar to alpha and beta particles using the electric and magnetic field? If so, if not, give reason. If so, give reason for that. Is it possible to deflect gamma radiations in a way similar to alpha and beta particles? Let's go, guys. Let me know what is the answer in the comment section. That is it from my side. Once again, the coupon code is AME Pro to avail the 50% discount. It is only going to be valid for the next couple of days, so make sure to check that out. And yes, do not forget to like, share, and subscribe, guys. I'll see you guys in the next one. Take care of yourselves, stay safe, and adios, people. All the best for your exams. Do well, rock it, enjoy your studies, have a lot of fun.